All right. In this example, right, let's see what happens, right, when a rod sticks and rotates, or one where it sticks or rebounds. Excuse me. Right? Well, very simple conceptually. Okay, which one is going to take more torque? Okay? Well, to stop a ball, okay, acceleration, okay, equals a change in velocity over time. So on this one, my change in velocity would have to be -4 meters per second. Over here, my acceleration is going to be -6. I go from 4 to 2, the opposite direction. Right? Again, assuming they win the same time, the one on the right is going to have a greater acceleration. So then if we looked at F net, okay, equals ma, greater acceleration, greater F net. Okay? So it's going to rotate faster when you rebound. Again, forces is going to be able to answer so many of these questions. Now, this one says if the ball strikes the rod 25 centimeters from the bottom, how fast will it rotate after the collision? Okay? So on this one, which one do we want to solve? Let's solve sticking first. Okay, maybe we'll do both to prove it. Okay, so I have it sticking. So on this one, okay, what are my net forces? Okay, well, again, we have force of rod on ball, force of ball on rod, and then we also have force of pin on rod. Okay. Again, the same forces. So again, I have 3 equal and opposite forces. F net, I've written this so many times, but you should do the same, does not equal 0, so the change in momentum does not equal 0, so momentum is not conserved. But torque net, in this scenario, it does equal 0 because these have equal forces, equal lever arm, and then this force, okay, at the top does 0 torque because force goes through the axis of rotation. So angular momentum is conserved here. So if the change in momentum is 0, then I can do Li equals Lf. So what has angular momentum beforehand? Okay. Well, nothing is rotating, but I have an object moving at a velocity, so it has linear momentum and it has an r. Okay. So I could say the angular momentum of the ball plus angular momentum of the rod must equal, and if they stick, we say we can look at them as a total. So the ball, okay, if it's linear, we said is momentum times r perpendicular. The rod, well, the rod is not rotating, so it has 0 angular momentum. Afterwards, they stick together, so I have to look at it I as a system times omega final. All right, let's now put in our terms. We don't know momentum, so I could then look at this in terms of mvr equals, we don't know I total, so this is going to be mr squared of the ball plus, it tells me 1/3 ml squared for the rod times omega final. Okay. All right, what is my mass here? My mass is 4 meters per second. Not 4, my mass is 2 kilograms. That's the wrong unit. Good thing I was saying the units. The velocity is 4, and it's positive. Always double check that. The R, we're going to say is, where is it acting at? 25 meters from the bottom, so that's up. So it's 1, so this is going to be 0.75 meters equals my mass of the ball, which is again 2 kilograms, times its R, which we just said is 0.75 meters squared, plus 1/3 mass of the rod, which is 3 kilograms, times the L, it's the whole length, 1 meter squared. And all of that is multiplied by omega final. take a second, pause yours, and all right, so here's my math, and I ended up with omega final equals 2.82. Again, how could you check to see that this compares to the other one? So this was over here if it sticks. Right? Let's do the other one if it doesn't stick. So this would be, again, Li equals Lf. So I have the ball, which is the same, that doesn't change, plus L of the rod, that doesn't change, equals, now it's not L total. Now we have L of the ball afterwards plus L of the rod afterwards. So this side is the same. Nothing will change. I'll have the exact same numbers, but this side's going to be a little different. L of the ball is now going to be mv times r perpendicular plus I of the rod times omega. So you guys can plug the numbers in and check to see that it actually works. The big thing you got to watch out for is this velocity. What is that velocity going to be from the picture? It has to be -2. So that's going to be a negative number. So if I had to solve for I of the rod, it's going to be my initial value that I had before, and this is going to be a negative number, so you'd have to add L of the ball. Now it's not the same L of the ball. You're going to add L of the ball final to the other side. So this answer is going to be larger. You're still going to divide by, well, I guess even a smaller number, so your omega final should go up, and that's what we said in the previous one that you'd have there. Just another way to prove it. If you want to practice your math skills, which would be a wonderful idea, or just practice finishing throwing the problems, give it a shot.